Hello, everyone. Thank you very much for this very spectacular introduction with special effects. I'm a medical physicist, so then we have a wide bunch of professions today. And I'm going to talk to you about anthropomorphic phantoms that we use for medical imaging analysis, and they are based on 3D printing. I hope I don't have too many equations. I will try to go a bit fast for the sake of time, so maybe some slides you will see flying your way, but some of the things we're going to talk about have been already mentioned, especially for the physics and micro-CT imaging. So, okay, let's start. So the basic things I'm going to touch on today, because it's not a long presentation, is a basic introduction about what is CT imaging, the main differences between medical CT and micro-CT, a bit about what are we interested in terms of image quality from the physics point of view in radiology, and what we understand that diagnostic image quality means. Then I will talk about phantoms. Phantoms are the test objects that we use to assess the performance of medical imaging devices. And I will also talk a bit about the workflow that we use to design and manufacture anthropomorphic phantoms, especially a lung vessel phantom that you will see, and that we obtain images based on micro-CT here in CWI. And finally, again, the wish list, because I realize that all the speakers have a wish list after all. And I think I'm very short, so I think I don't block your sight at any point, so I will stay here. If at the back you cannot hear me, just let me know in case I move a bit far from, just raise your hand and I will know what it is. And let's start. This I will skip. So, okay, what is a CT system? Very basic. We have an X-ray tube. We also have some filtration that is going to adapt the X-ray beam depending on the size of the patient, the part of the body we're going to scan. And then in synchrony with the X-ray tube, we have an array of detectors that is going to be rotating around the patient. And we also have a table that is moving, introducing basically the patient into the scanner. We normally scan humans, but sometimes we also scan things that are not human at all. For instance, dinosaur bones with someone that is here in the room on the third row. So I want to mention this because even though CT imaging and radiology, it's calibrated to human tissues imaging, sometimes we put things in the scanner for which the system is not calibrated. So that relates to micro-CT imaging to some extent. So then, here in the FleXRay Lab, we did some micro-CT imaging with them. In particular, here you can see, or maybe not, just what they've showed several times, the detector, also the X-ray tube, and in the middle there are a few very tiny samples with 3D printed materials, because we were trying to find materials as candidates to use for surrogates of tissues in the phantoms we are making. And this is the type of objects that I develop. This is a very small lung vessels. It's an insert that you can put into a thorax-shaped thing to mimic basically the full thorax of the patient. And it's used for quality assurance. You will see it in more detail, so you don't need to squint your eyes to try to see what it looks like. What physical properties are we measuring in CT? So what are the pixel values representing? They are related to the attenuation and the density of the materials that we have inside the scanner, as it's been mentioned by the previous speaker. So then, basically, in CT, it's sort of quantitative. Why? Because we have a scale range for the pixel values that we have. It's centered in water, that is always 0 in the image. So if you have a CT image of an object, and then you go through the pixel values that you have, if you measure something around 0, you know that the composition and the density is similar to water. It goes from positive to negative. So if you have very high values, it means that your material is very attenuating, for instance, bone in a patient. And if it's very negative, it means that it attenuates radiation less than water, for instance, air inside the lungs. And it's to be noted that CT values in the images, for the same material, they are going to depend on the X-ray spectrum energy. So depending on the KB that we use, then the pixel values are going to be changing. This is important when we are trying to benchmark CT imaging, for instance, with micro-CT imaging, because our X-ray beam is going to be different. So some differences between medical imaging and then micro-CT. In medical imaging, our main target is the human body. So then we need to have a calibration of the materials that we normally find inside the human. In micro-CT, you are scanning anything, a wide range of objects, from insects, minerals, tissue samples, industrial applications. So then the range of attenuations that you may encounter, sizes, is very, very wide. In medical imaging, the field of view is usually adapted to your patient size and also the scanned body part that you have. And then in micro-CT, you're normally limited and only can scan small objects, or you need to be very smart with the positioning that you have. The KB that we use is also different. That has implications about how penetrating are the photons, and then the level of contrast that you can actually get on the images, depending on the material you have. And normally also the X-ray tube output in micro-CT is far lower than what you have in medical imaging. That also has implications for for image quality. Sorry. And of course, the main difference also is resolution. To give you an idea of the resolution we have now in CT, the best one, the smaller detector that you can have, is between 0.5 and for ultra high resolution, 0.25 millimeters. And for micro-CT, the resolution is, of course, of the other microns. So it's several orders of scale smaller. So let's look at some images. As a physicist, we are interested in trying to measure, establish how reliable is a system, how consistent it is, and if it's generating the images in a reliable way. And then we use some test objects. The basic ones are called geometric phantoms, and you can see that they don't resemble the patient. They are basically cylinders made of plastic with different structures that we can use to measure certain image quality parameters. These are the most used ones in quality control by medical physicists all over the world. But then what happens that they are limited, of course. These phantoms are only meant to be measuring things in 2D, for instance, but of course the anatomy and the patient doesn't look like these cylinders I've shown you. We also have progressively systems that are more and more complex. For instance, in CT, now we have automatic exposure control. So then if you have a bigger patient or a smaller patient, the system is going to deliver a different output to generate your images. In image reconstruction, things have become very, very interesting in the past few years, because we've gone from basic field-level projection to iterative reconstruction and now even deep learning-based reconstruction. These latter algorithms, they are usually trained with patient data. So then to be able to evaluate these technologies, you really need to put in the scanner something that resembles the patient. So the phantoms I've shown you before, they are still useful for in basic analysis of the scanner performance, but we need far more than what they can offer. So for instance, how can we translate the measurements we do as physicists in objects like the one you see to what the radiologist actually has to detect on the images in terms of diagnosis? So this is the bridge that we need to cross between technical image quality and then diagnostic image quality. One step that we can have is to try to make our simple geometric phantom a bit more anthropomorphic. So then sometimes you can put rings around it to make it more like a thorax, increase the attenuation, and so on. And there are different approaches by different manufacturers about this. A next step that we have is anthropomorphic phantoms. You can see here an example. This one, in fact, the interior is a real skeleton from a human, and then the outside is cut in a plastic. But you can see in the CT image on the right that even though, yeah, you have organs and so on, it's not realistic. You don't have really texture. It's just based on uniform materials. So the human body inside is far more complex. Then in the market, we have also more realistic anthropomorphic phantoms, like this you can see here. But one of the problems they have is that usually they are very expensive, they are not portable, and then you are only tied to having one anatomy to test everything. So then, as physicists, when we are trying to evaluate image quality in radiology, we're on one side of the bridge, and then we perform certain, no equations here, don't be scared, certain measurements on the images to try to determine baseline and how the system is performing. And then at the other side, we have the radiologist that needs certain level of image quality to be able to perform the diagnosis. So how do we match these two parts? So we need anthropomorphic phantoms, and these phantoms need to mimic the attenuation, the anatomical distribution, and the patient total attenuation and shape. And if possible, we would like to have also relevant lesion surrogates or disease stages. And to make things even more interesting, till very recently, we were just optimizing image quality for human eyes, because the radiologist or the doctor was the only ones looking at the images. But now we have automated systems looking at the images, even AI-based. So what do these algorithms perceive in the images? What is good image quality for such algorithms? So then we need to combine complex anthropomorphic phantoms with some clinically relevant tasks that should be translated into an objective measurement of image quality. How can we do that? So one of the things I investigate is using 3D printing to try to create these test objects that we're going to use instead of the patient, because we cannot scan the patient as many times as we want. And also, having an object that you know exactly the structure and you know the design can help you to try to see how image quality is going to degrade or improve depending on what you select on the scanner. When did 3D printing start? So it was started by Charles Hull, and he started many, many years back. And basically, he was interested in injection molds for plastics. And then usually they were very tedious, and then it was not a repeatable process. So then he investigated and found out that you could use certain plastics and then UV coating for them to try to make them harder layer by layer. And that was the base of the first techniques of 3D printing, in particular for stereolithography. What applications do we have of 3D printing in medical imaging and also radiotherapy? So you can have them to design, for instance, example models that you can show a surgeon or a patient to explain how a procedure is going to be or to plan it. You can also use it to train doctors about what normal or abnormal anatomy looks like inside the patient. And you can also use it for prosthesis. This is something that is really growing in the past years because there are many materials that are biocompatible. So 3D printing is a field that is really, really growing in all fields that you can think of inside of medicine and radiology. And the one I'm interested in particular, is to make these type of test objects or anthropomorphic phantoms. So how can we make such phantoms? We have two options. We can have CT images of patients, make a segmentation, and use that as our model that we're going to 3D print. Or you can make a mathematical model where you have full control over the design of your object, and that is the object that you will print. And in my group, we go for the latter option. And I'm going to be talking especially about a specific object that we made with a 3D printing plastic, but I want to point out that also there are groups working with paper and coatings. And you can see here it's not a patient, it's actually a phantom based on patient images, generated by a group and a company called PhantomX. And it's extremely realistic. So as I said, this is a technology that is really exploding and growing for image quality assessment. And I'm going to talk, of course, about what we do, but as I said, there are many, many groups doing things. So then if you are curious, you can see different applications for this type of phantoms in other imaging modalities. So I'm going to take a breather, sorry. How did this start? So in 2015, I was hired as a postdoc. That was when I moved here to the Netherlands for a project called CLUES. And then in this project, we wanted to design on one side a basic or simple and portable anthropomorphic phantoms, in particular for lung CT and also for breast imaging, based on 3D printing. And we also developed some image quality metrics to go with them that I'm not going to go into this presentation. And right now I have a VENI project, and I'm interested in how to optimize the imaging chain when your observer is not human. So then for that, one of the things I do is to develop, again, anthropomorphic objects that can be used as a surrogate of the patient, and do all sorts of tests with them to try to see how the CAD or the radiologist looks at the images and what they can detect or perceive depending on the protocol we select on the CT. So what did we want with these phantoms that we want to develop? We want an anthropomorphic phantom for CT image quality assessment, and it should be portable and designed for a specific diagnostic task. We looked into thorax imaging because it's one of the modes that you can scan the patients that affects more patients. It's one of the most popular ones. Lung vessel detection and quantification is also used to determine patient diagnosis, and this is a stage and evolution. And in my group, they also developed these automated methods. And the diagnostic tasks, either on patients or in the phantoms, they can be either performed by humans or by these automated algorithms. If you have a test object where the ground truth is known, for instance, our custom models, this can help you to analyze the influence of different acquisition and reconstruction parameters in the output of your observer, either a human or a computer-based one. And these phantoms can be used for quality assurance of CT systems. You can also use them to benchmark these different protocols, because it's, of course, the same patient that you can take to different places. And you can, of course, combine the phantom I'm going to show you also with lesions as surrogates of lung nodules for different indications. So when you start doing things in 3D printing, especially for medical imaging applications, what do you need to look for? So you need to figure out what materials are you going to choose, and these materials need to mimic, to some extent, the X-ray attenuation of the target tissue that you want to mimic. It makes no sense that you use a material that attenuates a lot, for instance, like bone, to mimic lung vessels. Metals, normally they are forbidden unless you are interested in metal artifacts, even though you can use nowadays some 3D printing techniques with powder material that you have a small doping of metals, and then you can increase the attenuation of them to have a wider range of attenuations. Multi-material printing is still under development, besides the specific case I showed you with the paper and the doped ink, because I would consider that multi-material printing. And the image quality phantoms, they are very niche in 3D printing. So normally when you have your model and you go to a regular provider, you need to explain them a lot what you need so that they don't do any post-processing that is going to affect the model that you have created. Normally these materials are plastic-based, and for the chemist in the house, the same commercial name for a plastic, it doesn't mean that the attenuation of that plastic is going to be the same. You can buy two AVS from different providers, and then they can look totally different when you scan them, because you only know the commercial name of the basic polymer chain, basically. But they have dopings and different other alterations to make them more durable, to make them more hydrophobic, whatever. So it's important always to do test rounds of the materials you're going to be using for the printing. How do you start? So normally getting small samples, then you normally go for cubes, you put them in your scanner, you scan them, measure regions of interest, and you try to identify what materials your candidates could be similar to in terms of tissue. There are more and more initiatives to try to have libraries of materials in 3D printing providers, because as I said, there's a wide variety, so then in the community we need more knowledge shared about this. Going about our model. How did we do it? This started by a colleague of mine called Hilden Harder, and then he implemented a mathematical algorithm based on some morphometry studies by Dr. Wavell, in which they use specimens of human lungs, and they cast some molds, and they found mathematical models to try to describe how the lung vessels decreased in length and diameter as they went closer to the pleura. So then what my colleague did was to implement such equations in MATLAB in an algorithm, and then we made it in a way that the model grew in a constrained way inside an ellipse, because as I said, we wanted to have a model that was small and portable. Then this mathematical model, when you get the output, that is basically a 3D object, you can translate it into an STL file. Basically, that's the input language that you are going to use for your 3D printer. And then this particular object, we use a project HD3000. We selected a material that was called VCET EX200, and you can see here some of the specifications of it. And the smallest vessels you can see in our phantom, they are 0.2 millimeters in diameter. And that is below the resolution of regular CT imaging in radiology nowadays. So what does the phantom look like? At the left, you have the model output, and on the right, you have a renderization, so you can see the level of complexity and detail that our model in theory had. Now we need to see if this model was correctly printed, or if some vessels broke, or some parts didn't succeed. If you want to see it more in detail, here is a zoom part. Again, this is still the mathematical model that we developed. This is what it looks like. So a lot of vessels there. And this is the 3D printed object. And this is a zoom in part. So then one of the questions we have is, okay, I had the model, I know what it looked like, I have the 3D printed version of it, but how can I actually do a quality control of the 3D printed object that I have? How can I make sure that the vessels that I've defined in my model in terms of the location and also their sizes, their diameter, are what the printer has provided me? For this, we will go for micro-CT imaging. We inserted the lung phantom into a thorax-shaped holder. This will come in handy later because, of course, we want to try to mimic similar conditions to what we would have when we put a patient in the scanner. And if you want more details, then you can have a look at the paper where we talk about the equations and all that kind of stuff of the production of the phantom. One of the problems that you may find when you go for 3D printing is that even for the same printer, when you select different materials and the same technique, you have different possible resolutions. Here you can see for the same object that I just showed you, when the model shows in green, it means that it is hopefully going to be printed successfully, and this is for material 1, for a specific printer I'm not going to mention. And this is for another material that is very close in attenuation. So you can see that even on the simulation, many of the vessels would not be printed properly. So you have many drawbacks when you try to translate your models into practice. I just wanted to show you this slide for that. And this is what images of the phantom look like when you actually put them in a scanner. This is for field depth projection on extremely low dose. You can see that there are plenty of artifacts and also that the vessels are rather blurry. This is with iterative reconstruction because reconstruction has advanced a lot. Then I'm curious with Marta if she has scanned something in modern CTs because it changed a lot and now we don't have a screen film anymore, thank God. And this is with deep learning. And I'm going to show you now some zoomed in images. You've seen the level of detail of the vessels that we have in the phantom. We went for very small vessels because we wanted to be in the threshold of the actual resolution of CT systems used in practice. And you can see that the vessels, especially the small ones, they are blurry. Why is it important to have objects like these? Because we know what is in the phantom, in fact. So if we can benchmark what we have in the phantom to what the CT system is providing us, we can assess the level of image quality that we have. But the problem, what is our phantom gold standard? Our design file, you can take that, but of course, in the process of manufacturing, things can have gone wrong for some parts of the phantom, or maybe, as I showed you, for certain material you had more breakage, and you don't have any control over that. You just get your phantom as it is. And also with time, your phantom may have had some issues. For instance, one of these phantoms I always kept in a box, and suddenly you found some vessels flying over there, and you didn't know where those vessels were first. So it's very important to have a robust gold standard of your phantom. Why 3D printing and micro-CT make sense? Because with micro-CT you can look really in depth into the samples that you are obtaining. This is a pilot that I made together with some colleagues in Madrid with a very small and simple object. And I'm going to show you now what we did with CWI here in the Flex Lab. So here you can see an example of the segmented mathematical model on your left, and on the right a CT image with a filter that is a bit blurry. When we just try to threshold the images of one of the lungs here, you can see that it's very, very blurry, and then the vessels are not sharp at all. Let's look at what these images look like in a state-of-the-art CT and also in macro-CT to create our gold standard. So, in the middle of the pandemic, I think, is when we met the guys at CWI. So it was a while till I could come here with my phantom to be able to scan. And we came here together. They were very nice to enable us to scan. And then thanks to Tristan, and then especially thanks to Felix and Jan, we could obtain a micro-CT image of our phantom. And we weren't too ambitious in terms of the resolution that we went for at first, because it was a pilot. So we went even only for 0.1 millimeters in resolution, but that is even below the smaller sizes that we have in the phantom. And here you can see what the micro-CT looks like. If you remember a bit what the model looked like, it's a very nice resemblance. So the micro-CT we can actually use to define our gold standard for the object that we have produced. This is again the mathematical model compared to the micro-CT, just to give you an idea of what it looks like. And you can already see there that there are some gaps. So now what we are working on is to try to make a solid 3D registration of the mathematical model and the micro-CT to try to find the parts of the phantom that were not actually printed correctly. So this is the micro-CT image that we had. And you've seen not a great scan of the phantom, but to give you an idea of what this object would look in a commercial CT. What happens when we go to the future a bit, what CT imaging is going to look like, and it's already in our hospitals, like photon counting. This is what happens. So this is what our phantom looks like when we scan it in a photon counting system that they have in Erasmus. So that's what really convinced me that we really have more and more detailed and complex phantoms to be able to determine the image quality that these new systems can provide. Because if you have very simple objects, there's no way that you can evaluate these systems. And this is going to be presented this summer. So some things that are still work in progress, or the wish list, as we were talking. For me, especially, it would be making micro-CT more quantifiable, the quantification, because here you can see some histograms of exactly the same object, our phantom, in a micro-CT, the state-of-the-art CT, and also a photon counting CT, and you can see that the range of gray values that we have in the images is very different, and also the distances between them. So this makes difficult sometimes to distinguish materials that are closer in attenuation and properties, especially in micro-CT. And this links with what we saw earlier on about the spectral micro-CT. That would be really great. We also, or I'm interested in trying to push that micro-CT is used for quality control of 3D printed phantoms, because as I said, they are becoming more and more popular, and I really think that we need to work on that. And the final one is, okay, what the future, what I would like to see. So as I said, I would like to see micro-CT more quantitative. I also would like to expand the pixel value range that we can see in the images if we can, because then we could have more materials inside our phantoms. The establishment of quality control for micro-CT, in particular to evaluate these kind of objects, because you would need to decide how to position, how many projections, the dose, the filtration. You could also improve the reconstruction. And also, we need methods to benchmark the mathematical models to the micro-CT images that we obtain. So to try again to establish a robust gold standard based on micro-CT. And of course, the phantoms I've shown you, you can also use them to evaluate micro-CT technology. If you have different reconstruction methods in micro-CT, you have an object that you know the gold standard, you know what it is like, so you can use it to objectively measure image quality in your micro-CT too, and evaluate technology. And finally, I think that for this to stick, we really need to optimize the micro-CT imaging, to have a balance between the time and the results that you want to obtain, depending on the intended use that you have of the object you are scanning. And with that, I thank you very much.
Yeah, thanks a lot. Say we have time for 1 or 2 or 3 quick questions before drinks are waiting for us outside. Does anyone have a quick question?
I have a question, but thank you.
Yeah.
So my question is, so you mentioned that the goal of the VEI was also to look at optimizing, oh no, it magically works, that's strange, for AI-based methods rather than radiologists. Yeah. And this had me wondering, have you already come across a case where tuning the scanner for a deep learning method really led to a different setup than when you did it with a radiologist?
I'm working on it, not yet, because the thing is that we expected that AI applications would be inception faster. So in our hospital, we don't have so much access to AI applications. I expected when I submitted the penny that would happen, but then COVID came the way. What I'm interested in, so we've made some tests with not AI-based algorithms, but old school, but very robust segmentation algorithms. So I think even for radiologists, when you look at a protocol, you have different reconstructions depending on what they need to look at. So I believe that in the future we will have maybe different reconstructions for AI algorithms that are going to look at the images and that kind of stuff. I think that is going to be the future. And then you would have, they don't look at the same things in the image at all. They deal with different layers of information there.
Yeah. Okay, thank you.
It's thorough. Thanks for the nice presentation and also the insights on the different outcomes from different CT scanners on the gray values, and that's where my question starts. So if I remember my education correctly, the medical CT scanners usually work with Hounsfield units, yep. And they also are commissioned by a standard institute, and you get a phantom, and then you should arrive at the same Hounsfield units. So I presume that the fix for your problem would be to use the same phantoms and reach the same Hounsfield units, and then just like work with that standard instead of working with the gray values.
And that is the way we normally do quality assurance and acceptance of systems, but the problem we have is that those phantoms only contain like a selection of type materials that, by the way, you don't find inside the body. So they are materials that in density, you, for instance, use Teflon as a surrogate of bone, but it's not the same thing. So I think that first those materials need to be updated, because especially with deep learning reconstruction or iterative reconstruction, sometimes you don't get the same pixel values, and maybe it's because in the scanogram, in the raw data, there are differences that you cannot really get with FBP, so that makes sense. And then also if you compare to manufacturers, if they are correctly calibrated, they should work within a specification. So then a liver is going to look very different in different scanners, hopefully. Otherwise, something is going wrong with one of them. What changes is the histogram that you are seeing. It's like what I showed you in the image of the lung phantom. The pixel values are correct, but then you have a blurring that really makes that you have a less sharp image, and then you can detect the vessels worse. And that is related to the clinical image quality level. So it's a combination of both.
So you're going to update a new phantom and start a new calibration method?
I believe in revolution. That sounds very weird, but to be honest, I'm very embedded in the medical imaging community, and the phantoms we use, they were designed 30 or 40 years ago. So I really think, and manufacturers are aware of that, so they are also looking, some phantom traditional manufacturers are looking into 3D printing or other things, so it's not that this is the only solution. But the system is used now. I look of it as a person. That shows how much time I spend scanning. It is really used to have something human-like inside, and it's adapted to that, and it's optimized for that. So I think that we really need to go in that direction, and then keep the basic metrics to measure stability and that kind of stuff. They are still useful, but we need to go one step beyond. Otherwise, we have blind spots in performance.
Thanks.
You're welcome. Oh.
Anyone else? We're going to try this one?
Oh. That's brave.
Great. Okay, thank you. Yeah, thank you for the very nice talk. If I dream about this, I see this actually as a step somewhere in the middle, and I'm very curious how you feel about this. So yes, I fully agree. We need different phantoms to train machine learning algorithms. But in a way, this is still very cumbersome, right? You have to print all the different phantoms. It's difficult. Now, and I have this fantasy, and no one has been able to tell me whether it's right or wrong or feasible in 20 years or 30 years. So in light imaging, we have an LCD screen, and you have this matrix, and the light goes through, and you have stuff with polarization, and the transmission can be automatically switched on or off per pixel. If we would have something like that in X-ray, and not in a plane, but in a cube with voxels, would we be able to have a switchable phantom, like you print now, that we can link to a computer? And I'm specifically thinking of the FleXRay, where we moved from, let's say, the static loop of scanning and then inspecting and so on, to the real-time loop.
I would need a paper to make a scheme of what you said, Joost. One thing that I know for sure is going to happen, because manufacturers are working on that for phantoms. They are working on materials that they change their properties depending on an interaction. For instance, with electricity, they produce heat, whatever you can think of. So they are working a lot in that direction. So I think that they could also work in a line where your phantom could also react in different ways depending on the energy of the photons, for instance, that is hitting them and that kind of stuff. And that is linked to the doping, that I think is also the future of this type of materials. Ideally, I'm not sure if we could have a phantom, because the basic anatomy or structure would be the same even if you switch off certain parts.
Yeah.
So I'm not sure if it would work that way, but I'm also aware that you cannot really manufacture as many phantoms. This is ideal. I'm a researcher, I'm privileged, I can do these things, but you cannot have in a regular hospital 20 of these phantoms, no matter how cheap they are. I believe that we should have some standard anatomical phantoms that are detailed, and then go for virtual phantoms to test certain things in the CT, for instance. Because in the CT, you have different layers. In the same way as a micro CT, you have acquisition, you have reconstruction. If you only want to test reconstruction, then you don't really need to have a physical object there. You can also have a infinite set of different objects that you put there. For the acquisition, I think it would be complex, but as I said, it's in the past year, it's changed so much. They are doing very strange things with 3D printed materials because they want them to be, one manufacturer used the term, they want them to be alive. That I found a bit weird, but it also makes sense. They want them to be reactive to environmental conditions or any physical effect that you are putting on them. So maybe at some point that is feasible, but it's looking a lot in a crystal ball, Joost. So
yeah, but that's for your peachy grant, right? Okay, thanks a lot.
All right, I think with that, it's time to thank Irene and all of the speakers of the session one more time.